When we're studying for coding interviews, how do we decide what order we should study our different data structures in? For example, we know that we need to study strings, and we know that we need to study arrays. But we also know that strings are basically a form of an array, right? A string is just a character array. So if we study arrays first, that's going to make our strings a whole lot easier. Let's say that we also want to study dynamic programming. Well, dynamic programming is really based on recursion, right? Because dynamic programming, yes, there are bottom-up solutions, but for us to most easily understand it, we're going to want to start with recursion. And so we really probably want to study recursion before we study dynamic programming. We might also want to study trees because trees are a great way for us to understand how our dynamic programming is working and to see those overlapping subproblems. And we definitely want to study arrays because if we don't study arrays, then we're not going to understand how to cache our values in our dynamic programming. Finally, with trees, we probably want to study linked lists first, right? Because linked lists are basically a simple version of a tree, right? A linked list node is essentially a tree node with only one next. And so if we studied linked lists before we studied trees, that's going to make our lives a lot easier. So we have an idea of what depends on what, but how do we actually decide what order to study these in? Well, in this case, a possible order that we could do is we could do arrays and strings, then we could do linked lists, trees, recursion, and dynamic programming, right? That would be an order where we are always learning the prerequisite before we are learning the actual thing. But how did I actually figure this out? How did I figure out what order would be valid here? Well, in this case, what I really did is I just looked for things that didn't have any dependencies. And in this case, because I drew these arrows, something not having a dependency basically means there is nothing pointing out of that, right? Arrays don't point to anything, so it's not dependent on anything. And linked lists don't point to anything, so it's not dependent on anything. So I said arrays first, and we put arrays. And then once I took arrays, I see now arrays is no longer a dependency. So strings, we've already done what we needed to do with arrays. So now we can do strings second, right? We can add strings. And then once we do strings, that also gets removed. Now, when I look at these, the only other thing that I can do is going to be linked lists or recursion. So let's say I add linked list. That no longer is a dependency. That means that tree no longer has dependency. I can do trees. And then recursion. And then finally, I do dynamic programming at the end. Essentially, from a technical standpoint here, I'm just repeatedly looking for what is the thing that doesn't have any dependencies. I'm adding it to my result, and then I'm repeating. And the only case in which this would work is like, let's say that we had something like this. Now, if recursion is dependent on DP and DP is dependent on recursion, I'm not going to be able to get any sort of valid ordering because there's that circular dependency. And what we've essentially just done here is we've done topological sort. Topological sort is a really useful algorithm to use in your coding interviews anytime you need to figure out ordering with dependencies. So for example, the problem that we just looked at with sequencing our coding interview prep with dependencies, that is a great option for topological sort. Another example might be finding a proper build order where we have different packages that need to be built before other packages can be built. Now, we already went through this with our example of sequencing our coding interview prep, but the basic process that we're going to follow for topological sort is that we're going to look for anything that doesn't have dependencies, and then we are going to remove that. Basically, we're going to take that course, we're going to build that package, whatever it is, so that that is no longer a dependency. Then we remove that dependency and do that whole process again. Once we've gotten rid of one dependency, we look for the next thing that doesn't have any dependencies, and we repeat until we've either gone through everything or we end up with some sort of cycle. So let's go over to the computer and look at what the code looked like. Before we can implement our topological sort, we need to convert our graph data into an actual data structure that we can work with. In this case, I decided to use an adjacency list, and you can see how I converted the data that we were looking at into that adjacency list. Here you can see I mapped all the data structures to the indices 0 through 5, and then for each one, I'm using a set to store the indices of all the dependencies for that data structure. So in this case, strings is dependent on arrays. So I have the 1 in here, which is the index of arrays. Then arrays, linked lists, and recursion are not dependent on anything. So those don't have any edges. And then dynamic programming is dependent on a bunch of things, right? It's dependent on our arrays and our recursion and also our trees. And then finally, trees is dependent on linked lists. So with our graph defined using this adjacency list, we can now go and implement our topological sort. Remember that what we're going to do is find any node that doesn't have any dependencies. So So we're basically going to look for nodes that have these empty sets, and we're going to add those to our results. Then when we add them to the results, we're going to remove that as a dependency from all the other nodes and repeat that process until we've removed all the dependencies from all the nodes, or we get to a cycle. Looking at our actual code here, we're going to start by finding all the nodes that don't have any dependencies. These are going to be all of our possible starting points. Again, it doesn't matter what order we visit them in, since none of them will have any dependencies. In this particular example, remember that we have multiple possible places that we could start. But we'll add those all to our results. And then once we add them to the results, we go through each one. And as long as we have nodes that have no dependencies, we remove that node and add it to the results. And then we go through and remove it as a dependency from all of our other nodes. And finally, we'll check as we're removing the dependencies from each node, if that node has no more dependencies, now it is available for us to add to our results. Then finally, at the end, we just check, were we able to add everything to our results? If we get to a point where we weren't able to add everything, then that means that there was some sort of circular dependency in our graph, and so there wasn't a valid result. But otherwise, if we were able to add everything, then we will return our result. So if we actually run this with our data structures, again, here's the data that we have, and when I actually convert it to an adjacency list, it just looks like this. Let's run it and see what we get. In this case, you can see that the ordering that we got was first recursion, then linked lists, then trees, then arrays, then dynamic programming, and finally strings at the end. If we go through our dependencies, that makes sense, right? Because recursion doesn't have any dependencies, so it's fine for us to do that initially. Linked list also doesn't have any dependencies. Now 5, trees, is dependent on linked lists, but we've already studied linked lists, so it's fine to put that here. Arrays wasn't dependent on anything. Now dynamic programming was dependent on arrays, recursion, and trees, all of which we've covered here. And then finally at the end, strings was only dependent on arrays, which we studied here. And so this is a valid ordering. So now we have our basic topological sort, but let's look at another example that gets a little bit more complicated and is a little bit more interesting. This is a problem called the alien dictionary problem. And essentially what we're given is we're given a list of words that are in lexicographical order, right? They're basically in alphabetical order, except that we're told that the ordering of this alphabet is different from the English alphabet. Obviously, here we have words starting with W that come before words that start with E, which come before words that start with R, right? And so what we want to do is figure out what is the actual ordering of this alphabet. So in this case, the ordering of the alphabet would be W, E, R, T, F. Now at this point, your alarm bell should be ringing, right? Because we're actually told we need to find a valid ordering of these letters in the alphabet. And so as we've been talking about, that is a great use case for topological sort. So with this problem, we're not given the complete ordering of our letters. We're just given some specific dependencies. For example, we can see that W has to come before E because words that start with W come before words that start with E. So we can add that dependency. Now what else can we see? We see that T comes before F because WR is the same for both of these. And so the only difference between them is the T and the F. We also see that R comes before T because ER comes before ET. And finally, we can see that E comes before R. So now that we've constructed this graph, we just go through the process that we've been doing this whole time, right? We're just going to find the thing that doesn't have any dependencies, remove it as a dependency, and then repeat. So in this case, the one node that doesn't have any dependencies is this W, so that becomes our first value. And then we remove the W and remove all the dependencies. Next, we can add E because it doesn't have any dependencies, then R, then T, and finally F. So with this problem, you can see that once we're able to generate that graph, it's pretty easy to actually solve it because we're just doing the exact same topological sort that we were doing before. So the only challenge here is actually generating that graph in the first place. And let's go back over to the computer and I'll show you what the code looks like for that. So looking at this code, most of it is very similar to what we had before. The only big difference is these first couple lines here, right? Instead of taking in a graph, we're taking in a list of words, and then we have to generate that graph from those words. That was kind of what I was talking about on the whiteboard. Then once we do that, the rest of it's the same, right? We just find what has no dependencies, and then we loop through everything, removing those dependencies until we ultimately get something that either includes all the letters or does not include all the letters, right? And if it doesn't include all the letters, then we just return the empty string because that is what we do when we have an invalid alphabet, and otherwise we just join everything together. So let's look at the interesting part here, which is this generate alien graph. So to do this, we're just going to compare all pairs of words. First, I'm going to go ahead and initialize my adjacency list so all the words are in my graph. And then all I'm going to do is to compare sequential pairs of strings. Essentially, what I'm just doing is looking at what is the first character that is different between one string and the next string, and that is the character that is defining the alphabetical order. So anytime I find a pair that is different, that becomes my dependency, and I add that into my graph here. And then once I do that, I've generated that whole adjacency list, and then I use that to do my topological sort. So if we run our code here with these two examples, we get for the first one exactly what we got when we did it by hand. And in the second one, for AC, AB, ZC, and ZB, we can see that, okay, A has to come before Z, which it does, and B has to come after C, which it does. And then there's actually no connection between the A's and the Z's and the B's and the C's, right? We have no idea which comes first. And so for all intents and purposes, either version is valid in our dictionary. So there you have two different examples of how to use topological sort. Again, this is a super useful tool to use in your interviews, so I definitely recommend spending some time figuring this out and understanding how it works. And if you want lots more on graphs and graph problems that commonly come up in interviews, go check out this video on secret graph problems that interviewers love to ask, and I look forward to seeing you in the next video.